Today, we present our work 360 BEV, Panoramic Semantic Mapping for Indoor Bird's Eye View. The bird's eye view (BEV perception) is a commonly used process of obtaining allocentric maps from egocentric views. Since it clearly presents the location and the scale of objects so that is suitable for navigation tasks. However, BEV perception has not yet been extensively explored for indoor scenes. For semantically mapping these indoor scenes, the sequence-based method were proposed, which have to process whole videos with a moving camera. Compared with outdoor scenes, indoor scenes have less moving objects. Therefore, we intend to use one single sensor inputting a panoramic image to achieve the task of semantic indoor mapping. So the question is how to convert the front view information into the top view. Here I will briefly introduce you to these 5 paradigms based on previous work in general. Okay, our proposed method is based on the right figure, different from the left one projection before segmentation and the middle one projection after segmentation, which takes an intermediate state and project the feature map. To introduce a new approach that overcomes the limitations of existing methods for indoor semantic mapping, we propose a novel solution in this work. As shown in the figure on the left, current methods rely on computational, expensive processing of entire sequences from video frames and are constrained to synthetic simulators due to the lack of the real indoor datasets. However, these drawbacks restrict their suitability for real-world indoor semantic mapping. To address this issue, we introduced a new method called the 360 mapper, which achieves a panoramic semantic mapping for indoor BEV and is illustrated on the right. One key advantage of this approach is that it uses a single panoramic image to capture everything around the camera, avoiding the need for processing many video frames or using multi-cameras. Our own approach, it also follows an encoder-decoder structure, so transformer-based vision encoder for panoramas and inverse radio projection combined with reference points and the 360 attention modular. Then I want to introduce the proposed flexible projection method, the inverse radio projection IRP code, for which the input of a panoramic depth is included. We can easily obtain a top view mask map by projecting from depth information. This mask map is then used to generate a 3D reference point with a corresponding map height. Then these 3D reference points are projected onto the sphere to generate 2D reference indexes, as shown in the equation below, where index height and index weight represent the index values at the 2D reference for the height and width of the feature map, respectively. And the 2D reference indexes are then used to locate the corresponding feature points on the encoded front view feature map. Completing the projection as IRP, there will be still some problems. The first is there are some distortions in radio projection, and second, depth information has flows, and this point-to-point form will cause some errors. In order to eliminate the effects of distortions, as shown in the diagram below, instead of relying on multi-view features across multiple cameras, our 360 attention module is designed to directly adopt adaptive sampling offset and extract features from a single panoramic feature map. And the mask operation is applied to maintain the BEV query efficient and adaptive to front view panoramic features by using depth information as a bridge. For our experimental part, we will analyze the result of a multiple dataset into mainly 2 parts. At first, dataset preparation and Second, experimental results. The overall statistical information at the two datasets is shown in the table on the left. Besides, we further calculate the per-class pixel number and per-class frequency of the both BEV dataset in figure on the right. Here are the quantitative results. Two tables in the upper left corner show that the front view panoramic semantic segmentation, thanks to the 360 attention we proposed, our model is able to achieve state-of-the-art performance in both two datasets. And the another dataset, BEV Metapod, our model also achieved better performance by a clear margin. From the figure A and B presented, it is readily apparent that our model can better recognize the chairs and tables and the bird's-eye view semantic maps, yielding more than 6% IOU gains compared to the baseline transform map. Thanks to the IRP projection and the 360 attention, whether in the panoramic front view segmentation task or in the top view 360 BEV task, the results of our model are better. Take the lower right corner for example. In the last zoomed-in theme, 360 Mapper provides accurate semantic maps, such as in counter, chair, and wall categories, whereas a baseline transform map misclassifies them as tables and doors. And based on this qualitative analysis, our 360 Mapper can effectively handle object deformations and image distortions, yielding better BEV semantic maps. In conclusion, a new 360 BEV task is introduced for the first time to address indoor semantic mapping via a simple frame panoramic image and generate ground truths for this new task and also extend front view dataset. Also, a dedicated solution for indoor panoramic semantic mapping is proposed. Thank you.